Okay, so this recording is about reduction to linear form. So imagine we have this XY data shown here, and imagine that we have pairs of points where we have coordinates x and y, and we plot them on a scatter diagram as marked by x on this scatter diagram shown here. And then we get a regression line. This is a line of best fit. And we can do this on ClassWiz. Just look up the video on Moodle ClassWiz links and you'll see that there's an easy way of plugging in some XY data and getting the line of best fit, and you get the equation. And that enables you to, for a particular value of x, for a particular value of x, predict what the y value will be. And you're using the regression line to predict values. What I want to discuss today is what happens if instead of having data that appears to lie in a straight line, we instead have data that looks a bit like this, and we might have data that looks like it fits onto something, but it's probably more like a curve, yes? And then the question is, what kind of curve is that? Is that a curve of the form y equals a x to the b, where it's a power of x? So for example, y equals 3x to the 4, so it's a quartic. Or is it a form of y equals a b to the x, which is an exponential, something like, for example, y equals 2 times 3 to the x, yes? Both of which could possibly fit the data we see here. So if we put a line of best fit, we see it looks like it's a curve rather than a straight line. And that's what this part of chapter 14 is to help with possible relationships of these two types. That's exponential, this type here, and this I'll call polynomial, although it really isn't polynomial because the power b doesn't have to be a whole number. It could be a negative power or it could be a fractional power, but let's call it polynomial for the moment, or a power of x, and the second one is exponential. So the question is, if we have data, x and y data, that we suspect is of polynomial or exponential form, how can we check to see if it is or it isn't? And what you can do is you can get a logarithmic paper and you can plot the XY data on logarithmic paper and you can see if it fits to a straight line on logarithmic paper. But mathematicians don't need logarithmic paper. We can just use normal paper by doing the following, okay? So first of all, what happens if we suspect that it's of type y equals a x to the b? What we do is we take logarithms. It doesn't actually matter if we take logarithms to base 10, to base e, or to any other base. So I'm going to take just log of both sides. And when you don't write a logarithm base, it means it's base 10, but in my case, it's going to mean any base. So if I take a log of the left-hand side, I get log of y. If I take log of the right-hand side, I get log of ax to the b, so I get log of ax to the b. But if I simplify that using log rules, I get log of a plus log of x to the b. And then if I use the second rule to bring down the power of b, I get b log x, okay? And here, the variable y has become the variable log y, and the variable x has become the variable log x. The constant a has become the constant log a, and the constant b remains. So what does this suggest? This suggests that we should plot log y versus log x, and that we will find that the gradient of that line will give us the b, and the vertical intercept where the line crosses the vertical axis, the log y axis, will give us log a. Okay, and so what you do is that you plot not x against y, but you take, for each of the x values, you work out log of x, you work out each of your values, you work out log of y, you work out each of your values, you plot that curve, so you get a log x, a log y, you plot your new data, you work out the correlation coefficient, which tells you how close it lies to a straight line. You get the regression line, the line of best fit, and that will tell you what the equation of this line is. So suppose that you find that log of y equals, let's say, 2 plus, so the vertical intercept is, let's say, 2, and I suppose the gradient is 3. So plus 3 log x. So suppose we have the gradient equals 3 and the vertical intercept equals 2. We can therefore work out what the initial relationship was, because now taking the reverse process, we now see that log of a is 2 and that b is 3. Okay, and applying the reverse process, we get here that the 3 can come in as log of x cubed. If this is base 10, the 2 becomes log of 10 squared, and bringing them together, we get log of 10 squared x cubed, and that means that log of y equals log of 10 squared x cubed, which means that y equals 100 x cubed. Okay, if our gradient was 3 and our vertical intercept was 2. Or you can do it by simply saying, solving log of a equals 2 and b equals 3. Well, the b equals 3 gives us x cubed. And if you have log of a equals 2, then if log to base 10 of a equals 2, that means that a equals 10 to the 2, which is 100. Okay, so that is one possibility. Another possibility is that we investigate whether maybe the relationship is y equals a x to the b. So this is the logarithmic relationship. So what should we plot here? Well, if we take logs of both sides, we get log of y equals log of a x to the b. And using log rules, that means it's log of a plus log of x to the b. Bringing the power down, we get, I'm doing the same thing, aren't I? Yes, that was wrong, sorry, apologies. So it should be y equals a b to the x. So going through that logic again, we take log of the left-hand side and we get log of y. Log of the right-hand side, we get log of a b to the x is log of a plus log of b to the x. And then bringing the power down, we get the x coming down and we get log of b. So here, what we need to say is that the variables x and y have now become variables log y and x. And so we should plot log of y versus x. In other words, we should keep our x data as it is, take log of our y data. So for each y value, we take log of each of the y values, and now write them here. And now we plot our data, so where we have x and we have a log of y. And if we plot our data and get a straight line or something close to a straight line, we'll know that it's of this type. And then suppose that the gradient is some value. Suppose the gradient is 1.1 and the vertical intercept, suppose, is 2. What does that mean? Well, going back into our relationship, we write log of y equals a vertical intercept of 2 plus 1.1x. And you can now work out what a and b are in two ways. You can either say log of a equals 2, and so a equals whatever the base is. Let's suppose it's 10 to the 2, which is 100. And here, the log of b equals 1.1. So that means that b is 10 to the 1.1. Or you can use log rules in reverse. So here, this basically means that if we have log to base 10, we now treat the whole of the right-hand side as a single number. We get y equals 10 to the 2 plus 1.1x. And then using the laws of logarithms of powers, you get 10 to the 2 times 10 to the 1.1x. And so y equals 100 10 to the 1.1 to the x, and 10 to the 1.1 is about 12.59. So that means that A is 100, B is about 12.59, but is in fact 10 to the 1.1. And so we have an exponential relationship of 100 times 12.59 to the x. The numbers can change, but the ideas are the same. So for this part of the course, you should learn on ClassWiz how to get the line of best fit from some data. Check maybe on Desmos visually that actually works, because Desmos will also do a regression line. And then you need to be able to work with the relationships which are of the form y equals ax to the b, which is polynomial or power of x form, or relationships which we suspect are of exponential form, y equals a b to the x. In both cases, you take logs of both sides, and you plot either log of y against log of x, or log of y against x. Then you work out the gradient and the vertical intercept, and from those you can work out what the original coefficients a and b are. That's it.